Hey guys, Mr. Wilson here. Today we're going to talk about chords and arcs. At the end of this video, you should be able to understand the relationship between chords and arcs and central angles. And you should be able to find the missing links and justify how you get them. Okay? A chord is a segment whose endpoints are on the circle. Okay? And a chord that passes through the center of the circle is called a diameter. So we've dealt with chords before. Not a new concept. Now we're just dealing with different chords. Okay, in this circle, a diameter is represented by AB. Endpoints on the circle goes to the center is O. A radius is represented by, say, OC, center to the side, and a chord segment PQ. See that it goes two endpoints on the circle. All right, so some terms there. Make sure you look at those, get accustomed to those. Alright, so first theorem with chords. Within a circle, I'm going to scoot this up. Within a circle, congruent central angles have congruent arcs. Okay, something we already know. Congruent arcs will have congruent chords. Okay, and then congruent chords will have congruent central angles. So central angles and arcs we've already talked about. We see how they are related. Notice that relationship transfers over to chords as well. Okay, so a central angle in the same circle will have the same chord length if they're congruent. And so since that's true, then the chords and the central angles will be the same as well. Okay, so let's look at this diagram down here. It says that circle O is congruent to circle P, and they told us that arc BC is congruent to arc DF. So they're telling us basically that these two arcs BC, DF are the same. So the conclusions that we can make from that is if these arcs are the same, well then I know that the angle, the central angles, angle BOC is congruent to angle DPF. Central angles have to be the same as well. Okay, also if we know that the arcs are the same, then I know that chord BC is congruent to DF. Okay. Alright. Next example. Says use circle P to answer the questions. What information is given? Well, in this problem, they tell us that QS and RT are congruent. So RQS is congruent to arc RT. Okay, with this information, we can conclude that angle RPT, so this central angle here, corresponds with RT, should be the same as the central angle that corresponds with QS. So that's angle QPS. Okay, and then we can also see that this chord QS, we'll mark with double here, should be congruent to the chord that corresponds with arc RT. So chord RT. Okay, and it's like a segment. No, we call it a chord, still a segment. Okay, so just applying those theorems. Flip to the other side, then. Theorem 2 with chords. Okay, now it says within a circle, or congruent circles, chords equidistant from the center are congruent. Okay, in a circle, chords that are equidistant from the center are congruent. Okay, congruent chords are equidistant from the center. Okay, so it's really the same thing. As the other one is the converse statement. And so let's look at that. Our first example says find the value of A and explain. So here we're given perpendicular distance. Okay, and anytime we talk about distance, We're talking about a perpendicular distance. Remember, that means straight line to us. Basically, it means we're going the straightest way we can from one point to a line. And so we see that these two distances are the same. From this center to this chord, and from this center to this chord, PR, are both 9. So these chords are equidistant from the center. Since they are equidistant from the center, I have PQ is 12.5 and I have QR is 12.5. So this whole chord PR is 25. Since PR is the same distance from the center as this chord, we know that that has to be the same. And so I know that A is 25. Okay. PR and I'm going to name this so I can talk about it. And RS are equidistant from the center. Equidistant from center. Okay, and so that means we know that they're congruent. Alright, next problem, we have two chords given to us, where this chord is 18 and 18 here, so that means this chord is 36, and they tell us this chord is 36. Well, because we know this about the chords, move this around so I can stop fidgeting with paper. Because we know this about the chords are congruent. If the chords are congruent, we know that they have to be equidistant from the center. So how far away from the center is this one? Well, it's 16 away. So that means X also has to be 16 away. Since the chords are equidistant, since the chords are congruent, they are equidistant from the center. Equidistant from the center. Alright. Moving on from there, it says in a circle, a diameter that's perpendicular, a diameter that is perpendicular to a chord bisects the chord and its arcs. Okay, or radius. Okay. In a circle, a diameter that blanks a chord is perpendicular to the chord, so bisects a chord. So again, if it bisects it, we know it's perpendicular. If it's perpendicular, we know it bisects it. Okay, and then finally in a circle, I feel like I already recorded this. Perpendicular bisector of a chord contains perpendicular bisector of a chord contains the center. Okay, because those are diameters, right? Okay, so let's find these values then. We want to find the value of R. In this problem, look that they gave us LM as 14 centimeters, and so that's the whole chord. You see that KN is perpendicular to the chord, so we know it bisects that chord, so this is 7 and 7. So now to find R, we can use Pythagorean's theorem where we have two legs of a right triangle. So I can say that 7 squared plus 3 squared equals R squared. So 49 plus 9 is R squared. R squared is 58. R will be radical 58. Okay, I could do 2 times 29, but that's a prime number. Radical 58 is enough. I'm just going to type that here, radical 58, and that gives me 7.6. Okay. Okay, number 2. Again, notice that we have 11 here and 11 here, so that means that BC bisects this chord. Since it does bisect the chord, remember that if it bisects it, that means it's perpendicular to it. Okay? So it's a 90-degree angle, and now, again, we can use Pythagorean's theorem, and now we're using the hypotenuse and a leg to find the other leg. So we'll say 15 squared equals 11 squared plus y squared. So that's 225 minus 121. So when we do that, 225, 121 plus y squared, we get, subtract 121 from both sides, so we get 104 equals y squared. Solve for that, that's what, 57 times 2, which is, nope, not 57, 52 times 2. Let's break this down. So that's 4 times 26. That's 2 and 13. Okay, so we have 2 radical 26. Oops, 2. 2 radical 26. So y will equal 2 radical 26. As the decimal, again, we can just do that by punching that into our calculator. And that's what, 10.20, 10.2. Okay, and again, since we saw that the chord was bisected, we knew it was perpendicular, so we could use Pythagorean's theorem. All right, number 3. We want to find x. All right, here we see first that this is 90 degrees, so it's perpendicular, so we know that this bisects. And so since it bisects, what we can do is we can use Pythagorean's theorem to find this segment. I'll just call it y for right now because it's not x, but it's an unknown. And so we can use Pythagorean's theorem to find this segment. And so again, I'll use 6.8 squared equals 4 squared plus, say, y squared. 6.8 squared gives us 46.24. Gives us 16. So subtract that, we get 30.24 equals y squared. I'll take the square root of that. And so we get y to be 5 point, and I'll just make it 5.5. Okay. So y is 5.5. We see that there are 2 of those, so times 2, and that gives us 10.998. If we rounded it, we get x equals 11. Okay. So it says in number 3, find the distance from the midpoint of the chord to the midpoint of its minor arc. In number 3, find the distance from the midpoint of the chord to the midpoint of the minor arc. Sweet. So here we go. Here is our minor arc. This is the minor arc here. And so it's just making you think about the circle a little bit more. Not necessarily a challenging question as far as mathematically, but as far as conceptually, do we still understand that this is a circle? And yes, we do. So know that from the center to the midpoint of the arc, wherever this midpoint may be, you know, I'm making this point, but wherever this midpoint may be, okay, this thing is a radius. In a circle, what do we know about radii? Well, they're all the same. Okay? And so the radius is going to be 6.8. So from the center, the midpoint of the chord was 4. So the distance from here to here will be the difference between the radius and this length. And so 6.8 minus 4 is 2.8. Okay, so that's just understanding that, hey, we're still dealing with the circle. Radii and circle are congruent. All right, so there we have it. Dealing with chords and arcs, perpendicular, throwing in some Pythagorean theorem there, okay? Yeah, good stuff. See ya.